Okay, Algebra 1, this is chapter 4.7. We're going to talk about inverse linear functions. Guys, remember linear means straight lines, so usually it will mean that there's a positive correlation or negative correlation going on. As an input, you get an output. And you can have slope-intercept form, standard form, point-slope form, all different types of, or a couple different ways to write an equation. And you can have a graph, it's a line, you can have a table, set of points, and then those equations. So we're going to talk about how to find inverses of those. Guys, an inverse relation, guys, is a set of ordered pairs obtained by exchanging the x and y coordinates of each ordered pair. Basically, if I take a step, so if I start at A, so point A, and I go to point B, okay? The inverse is basically the opposite, and it brings me back. So we don't want to say opposite, because if I add, then I can subtract. That's like kind of the opposite. If I multiply, then I divide. So if I multiply something by 2, to get back to where I started, I'll divide by 2. So you're going to do the inverse operation. So when we talk about the inverse of adding, it's subtracting. The inverse of multiplying is dividing. The inverse of dividing is multiplying. Things like that. So the biggest thing about the first set here is we're going to give you a group of set of points or a table. And the coolest thing about it is if one relation contains a point or an element A comma B, then the inverse relationship will basically flip-flop those and put B comma A. So you basically are just saying switch x and y. It can be that easy. So in example 1 here, we have a point negative 6, 8, negative 15, 11, 9, 3, and 0, 6. So we're just going to switch them. And so I've got 4 points, and so I'm going to make a set of 4 points. And I'm just going to switch. Do not change any signs. It's 8, negative 6. It's 11, negative 15. It's 3, 9, and 6, 0. You are done. That's as easy as it gets. And so the same thing, doesn't matter if we're talking about a set of points or a table. Remember, this table here is just still an xy. And so all I have to do is create a new xy and just switch them. And it's that easy. Do not change any signs. Because if you graph these, you will end up finding that they are different lines and that you basically will undo what was done earlier. It's very cool. So, to graph an inverse relationship, you just need to say you're given a graph and your line looked like this. Actually, we'll change it. What if my line looked like this? Well, then I'm just going to use the tick marks and I'm going to find something that looks relatively nice. Like this point right here looks like 3, 3. And maybe something back here, which would be about here, negative 2, 2. And that doesn't work out. Yes, it does. It'll work out fine. Now here's the thing. 3, 3, guys. So I'm going to find some nice points on my line. I'm going to switch x and y and just plot the new ones. So I'll put those in red. So if I switch 3, 3, I still end up with 3, 3. So any point that is exactly the same as the other, you won't be able to tell the difference. The other one, which is negative 2, 2, will become positive 2, negative 2. So this point will be the same, but now we're going to talk about 2, negative 2, so therefore the line will go like this. It's actually really cool is when you actually plot a lot of these, you start to realize that there's a special line called y equals x. And that y equals x line, where y would be to equal x, like 3, 3, actually is reflected. So these are reflections of each other about this line. Like there's a mirror here. You could fold this graph in half and they would actually overlap there. So that's how you can take a graph, find nice points, switch them, and plot the new ones. And the last thing I want to do is, what if I gave you a line equation? How do you find the inverse? Well, here you go. If you are using function notation, like our problems here, we got f of x, change it to a y, please, because when we graph, we know x's and we know our y's. Once you have the y there, you can go to 2. I want you to switch x and y. Just switch places. Take the y's out, put in x, take the x out, put a y. And then just resolve for y. Then what we'll do is we have inverse function notation, and that's why they use a little -1 as a power on f. Does not mean take it to the -1 power, it's just a notation to say this one's the inverse of the original. So like f of x is the original, f inverse is inverse notation, and sometimes they'll actually leave it as y inverse, y with a little -1 on it. So I'm going to change it to y equals 4x minus 12. I got to switch x and y, so x equals 4 times y minus 12. And now I want to get this y by itself. To do that, I'm going to get rid of the 12. So I'm going to add 12 to both sides. So I get x plus 12 equals 4y. Again, I'm showing my work. I'm only doing one thing at a time, and then I have to divide everything by 4. Remember, it's the whole side. So this becomes y equals x over 4, because I'm going to split it up, and then 12 divided by 4 is 3. This y is really the inverse. So this would be f inverse of x, if I switch it around a little bit, to say x over 4, or 1/4 x, plus 3. So if you were to graph these, you would see that same kind of grouping or whatever happened here, with they would be crisscrossing at some point on the y equals x line. So that's really cool. So we can do the same thing. Pause the video, do this problem, and then see if you did it right. So y equals 1/3 x plus 7. X equals 1/3 y plus 7. Subtract 7. So I get 1/3 y equals x minus 7. And this time I got to get rid of a 1/3. So to get rid of a 1/3, I'm going to multiply both sides by 3. These cancel, y inverse, because that's the new y. And then I'm going to distribute in 3x minus 21. And you now have inverse linear function. Very cool. Your homework, guys, is 1 through 5. First two, real simple. Switch them up. The second one, or third and fourth one, find some nice points, switch them up. And then in 5 and 6, switch x and y, solve for y. Have a great day.